All right, thank you very much. So sorry if I wasn't as talkative in the morning session. I was trying to let Jeremy have the stage because he's much more familiar with the actual science behind things. I'm more of the developer programmer. So I can answer a lot of questions relating to the program, but the actual science I leave to him. So I'm going to try and cover some of the infrastructure related topics that he wasn't able to in his session. So to start, what is NanoHub? NanoHub is a repository for information of all different types, not just tools, but also like lectures and courses that are centered around nanotechnology. And so the goal is to really aggregate everyone and everything that has to do with nanotechnology in one place to make it easy for everyone to connect with each other and to really find the information that they want. So one type of resource, so you can see there's many different resources here, but the main type that we're focusing on are tools, because we think that there's a huge impact there, especially for people who are working in experimentation, to help them to actually do some simulation without having to go learn programming or do something time-consuming like that. So there was one way to access the tools, which was in this resource tools area. And each of these, when you go through this sort of chain, you can see that in the third panel, there's a highlighted link on the title. And so what that actually does is it'll take you to like the main page or the splash page for the tool. So here I'll show you NanoDDScats. And so this page is pretty important. It has a lot of interesting stuff relating to the tool on it. So of course you can launch the tool from here. Additionally, this is an open source tool, so you can download all of the code that we're using in its entirety just by clicking this download button. Additionally, we have some tabs that have useful information. So we have things like citations. So if I click that, it'll show what papers have been published using this tool. So this tool has its own DOI, and it can be cited in papers and things. So we have a few, and actually some of you here have papers in this list. Other useful areas are, as Jeremy mentioned, if you have questions about the tool, you can find that in the questions tab. And we try to answer as many of them as we can as quickly as possible. So you can see, although a lot of them say open, there's at least one response, which means that we've said something in response. Like either we're working on it, or this is a good idea, or we've got it. You just have to do this. Additionally, there's a wish list. So that's like if you want to see a new feature. We have one wish right now, which is for the eDDA, which is another solver method, which it's using DDScat, but this is using a slightly different formula. And the only reason we haven't implemented it yet is it's actually using an older DDScat. So there's some potential to put that in, but it's not like the main thing that we're working on right now. So back to the About page. So this is kind of an old tutorial, but we do have a video tutorial, which can help, especially with a lot of the questions you guys may have. And if we scroll to the bottom, so this is where I was saying, some of these are repeats of the references, just again. But at the very, very bottom, there's a way to cite this tool and this work. So this is how this would actually get into papers, is through this citation. And there's one last tab that I actually accidentally skipped, which is the supporting docs. And so in this one we have kind of a more up-to-date tutorial than the video, where we have a text-based tutorial in PDF. And additionally, we also have some practice exercises. So it may help to get, although we don't have a lot of time here, these exercises were taken from a summer school where students spend like a number of days actually learning this tool. I really feel the 30 minutes was, the pressure was really on to cover everything. And it takes some time to actually go through and run these things. And finally, there's also some just basics on plasmonics, but that's more for people who aren't in the field like all of you. So when a user decides they want to create a tool, what happens is NanoHub, it gives them this main page that they can fill out as they like. It gives them all those tabs where users can then connect with them and ask them things. Additionally, they get a coding repository. So this is like GitHub or any of these places, but it's local to Purdue. And so like inside of here, this is all the code that we use for the tool. And since it's open source, users should be able to see all of this, all the versioning, everything basically as it's updating, as it's happening. You can see exactly what we did in the code. Additionally, developers get a workspace. So this is a Linux-based workspace. And you probably didn't know, but the container that the tool is actually running in is a Linux-based workspace that's been really limited, so you can't do anything. So this is a developer version of it, so I actually have like a text editor and things like that. But basically, you can run almost any different coding package within this workspace because it's made for development and for running tools. So whether you have code in MATLAB or in Python or in R or whatever language you want to write in, you can pretty definitely import your script and have it be able to be run inside of a tool. So, and in DDSCAT we use TCL, we use Fortran 90, we use Python, a mixture of different languages to make it work. And it's all made possible by having just this ready set environment that's ready for developers. So finally, going back to the tool itself, I know that we didn't get to cover a couple things. So one of them was the periodic functions, or sorry, the periodic simulations. So I just ran a small cube in repetition in the y direction, just to show an example of basically what we're talking about is if my cube was this centerpiece, we give basically an extra half repetition of that image in repetition. And there's also, like the Rapture interface itself has a lot of tips and tricks to it. So for example, a lot of this is covered in our written tutorial as well. Like you can change things like intensity values. So if you see like, okay, most of this is like kind of greenish and yellowish, so I can like lower this value. There's nothing that I see that's red, at least in this view. And maybe I'll like lower it to like 0.9 or something. And so it'll redraw. And maybe since I see it's a lot of yellow, I'll put the lower bound up to like 0.87 or something like that. And so like you can really try to zero in on the areas you're looking at. There's some other options too, like ISO surfaces. So this is only using 2 divisions on that color map. But as you turn them up, it can really increase the specificity of what you're looking at. And so I know some of you guys have used this tool in the past. Just a little bit of background about what we've been doing recently. Well, a lot of the background algorithms have just been, like, as of like last week, we just completed removing a lot of conversions of files and things like that that would use a lot of memory. And additionally, NanoHub also upgraded our workspaces for DDSCAT specifically to have higher memory locally. And in addition to that, I thought it wasn't really clear in the first session, but if you run your simulations remotely, the local sessions, they have like a set amount, and so they will often, they'll run out of time or they'll run out of memory. But if you run it remotely, then there's an automatic algorithm that'll send it to one of Purdue's clusters, and it'll send it to somewhere where it's pretty much guaranteed to run, because we've done calculations, we have algorithms for how much memory and how much space these things should be taken. So definitely, if you're running something large or something intensive, you always want to be running it remotely. Another of the new features we added was the vector fields. And so this is kind of in its incubation stage right now still. So like as you can see, there's a lot of erroneous vectors that are kind of obscuring the actual image that I want to see. So this is something that part of working with NanoHub is asking them for features too. Like our users ask us for stuff, but we also are partnered with NanoHub, the developers of this interface that we're using. And so we can ask them for things. And so definitely, like for example, one thing on my list is going to be, like how can I put like a cut plane in here or something to, just let me look at the more interesting vectors. Kind of like with the ISO surface, I was able to change the limits. Unfortunately, for vector plots, there's something about the back end of it that it's not available yet. So, I mean, that's just part of the working process. They work with us, and they help us out with a lot of things and help us to develop. Another thing that we did recently was we actually unpacked a binary file that contained information about magnetic fields as well as the pointing vectors. So that's stuff that actually users who use DDSCAT normally, they can't access that. It's packed in a binary file that, for some reason, Drain and Flattau just decided they weren't going to give users that info. It's just going to be, packed in like a small file. I mean, maybe it's just because it's to save space or memory or runtime. But anyways, we picked it up, we opened it up, and We took everything out of it, and so our users now have this extra functionality that basic DDSCAT users that are using the interface, the text-based version, they don't have that. So again, we added the magnetic field, and there are vectors for the magnetic field as well. And the pointing vectors which are basically the cross product of the magnetic field and the electric field. So I think that covers a lot of the questions that I thought that may have been brought up in the first session. I think one other potentially confusing point was the light rotation. So if we look at Blender, so this was the 3D shape generator. We have there's an object in the startup Blender file, so you can see lit up is that's the Y polarization direction, and this is the incident light. So we have so one thing that we did, because Blender is open source, is we made our own buttons to basically run a bunch of routines inside of Blender. So that's what this list in the bottom left is, the one that it has like centering at origin, resetting lights, which are these basically the base directions of these lights, how they started out. Also rotating these lights, so there's like an easy way that we can move them around. And also the actual exporting of the object. So, and that reminded me of one other issue that came up in the first session was, especially with scaling shapes. So it's hard to, it's definitely hard for all users, myself included, to figure out what is the realistic size scale of the object. And so there's two ways to do this. One is at the beginning before you start, and the other one is you can measure it at the end after you're done. So when you first start, Jeremy showed you guys like there's a ruler in here. You can also check if you press the N key. So this is also in the written tutorial, so you don't have to remember that. But you can see like the scaling size. Like you can see a grid on the bottom here, but I mean the scaling size is telling you exactly. Let me select the cube. So this cube is like 2 by 2 by 2 Blender units exactly. So I'll just do a quick run through of this point specifically because I know it's really confusing. So if I have this cube, and I'm going to make it even simpler and make it a 1 by 1 by 1. And then I go to DDA convert. So when we choose the option to populate by using dipoles per unit draw space. So since my cube was 1 by 1 by 1, if I choose to have 15 points per unit, then that cube then becomes a 15 by 15 by 15 unit cube, or sorry, 15 by 15 by 15 point cube. And so it's like a two-part process. So in the beginning, there is no realistic scale. It's all geometrical and it's all relational. So the size of objects, like they're just volumes and contours. They don't actually have any scale to them. So once you actually discretize it, then after you've done that, then you have the opportunity to actually put a scale to it. So just to complete the idea of the example, sorry, this died. My internet's dead. But anyways, so yeah, I don't know, it's dead. I mean, just as I was saying, so you have a cube that's 1 Blender unit by 1 Blender unit by 1 Blender unit. So this is like, there's no unit attached. It's just geometrical, just relational to like that object and other objects in the scene too. And so you specify how many points are on each side of that cube, and everything else is defined by that ratio, essentially. So if I had like a sphere somewhere else with like a radius of 2 units, its radius is then going to be 30. So it's just a ratio that can persist throughout the entire system. And then you actually set the realistic scale of how many units are going to be in between each 2 points. So if I had a 15 point per edge cube that's 15 by 15 by 15, and I said I wanted 10 nanometers for each distance between points, then it's going to be 150 by 150 by 150 in terms of nanometers. And so this is at the beginning, if you want to determine the scale at the beginning. So there is another way to determine it at the end, which unfortunately is not available right now. Well, okay, there's a couple reasons why it's not available. It's not just because I'm not connected, but so there is an output that accidentally got removed in our last version, but will be back like basically as soon as I get back to work, where in the 3D plot. Sorry, I have to find it. My apologies. This is not set up, but well, anyways, I'll just go back to the session. Basically, there's a way to view the composition at the end of the simulation with scale in the Rapture 3D viewer, and so that's a way to look at it in post-processing. Yeah, it's frozen again. So yeah, I guess, I mean, if you guys have any feedback or questions right now, I guess I can try and field some of those right now and let you know, like especially anything that has to do with the program or the tool itself. The science questions I can try, but not expert on those. Yes.
Well, I have a user question. So I've seen that black screen now a couple times when I've been playing. Is that just because the internet keeps kicking me out?
No, that has to do, okay, so there's, yeah, that's a good point. I didn't cover that. The containers can be run in two different formats. They can either be run in HTML5 or in Java. So if you run it in Java, you won't get that problem. It's purely an HTML5 thing. It's like a timeout thing. Like if you're not looking at it for a while, or if it's just like sitting there for a while, it'll do that. And you basically just refresh the page and it comes back. But it's like an HTML issue or something like that.
Any other questions?
So sometimes you do calculations where you generate information on whatever the grid is that the DAA wants you to do. And then you'd like to be able to go in and then determine information on some other, usually it's like a plane that cuts through that grid in some funny way. Okay, and so, so we have these codes that that's just like interpolating in some sort of way, okay, so that you can generate information. But I guess the question is, I mean, is that something that, I mean, you have sometimes in some of the plots you make, it seems like you're generating information on surfaces that are not just the DDA grid. Is that what you're actually doing? And can the user modify that?
It's the cut planes.
Okay, yeah, okay, so we do have like a cut plane option where basically, like, I mean, everything is generated on a type of grid, but these cut planes are able to basically just extract data from a certain portion of it. They're currently, I mean, they're hard coded into the viewer interface to only be along X, Y, and Z. We can't do like, angular, diagonal, rotated planes, unfortunately.
Yeah, I mean, anyway, I just thought I'd throw that out because that's still a piece of code that somehow we have is useful. But if you want to calculate something like a field, you want to know what the fields are on some surface, but you don't want it to be the DDA grid, which sometimes is useful, then that's the sort of thing that we're looking for.
So we can add this.
Yeah, definitely. That's something we can look into adding. I know DDA, it has its. I mean, like we're getting more comfortable to messing with their code. Definitely by unpacking their binary and changing some of their stuff. I mean, it's open source, so that's the point of it. So if there's things that we want to change about it, that's definitely something that this project is, it's amenable to. It's something that we
it's really
can
a
do.
post-processing function where you already run the DDA calculation. You have all the information that program will generate. And then what you'd like to do is to interrogate that in some way or another.
So Joe, do you have this code? Do you guys have this code, open source? The code that does
We're, happy to give it away. It's just a matter of who would, I was thinking about who in my group is the expert on it's the usual problem maintaining the code for any length of time. But we were just talking about that the other day. There was some project we were doing where, having the ability to calculate, on a specific, location was something we have to be able to do. And of course, we do service enhancement factors, but we haven't done any of those service enhancement factors I talked about today. We haven't actually done any of those kind of calculations. Recently with DDA, we just
Any other questions? I know there are students in the audience if you had trouble running DDA scat, any things you ever wanted to complain about in the chat?
So we'll talk about memory. How do you decide the size?
I mean, we have algorithms that they determine whether you're using a near field or not, the size of your problem. Those are the main things that determine how much memory it's going to take. In terms of how much time it's going to take, that's actually something that we don't have a clear algorithm for because there's a lot of variables that go into that. For example, if you're running like a sweep of wavelengths, the last wavelength is going to take a much longer time, and it's been, I think Jeremy and one other student that was in Prashant's group proved that it was like an exponential increase in how much time it was going to take. So there's a couple different factors on time, so we didn't actually do any automatic algorithm there. The user has to set their own time. And that's a little bit unfortunate because a lot of users set like a really low ball time on how much resource they need. They may be like, all right, I only need like 2 days or something, and it ends up being something that needs like a week. So they waste resources for 2 days. But I think there's a couple of things that we need to that I'm trying to encourage users to do, which is for example, overestimate how much time it's going to take if you want to see that simulation come to an end, because the only cost is there's a queue for the remote simulations. So if you set that your simulation is going to take a long time, you might be lower back in the queue, but you're more guaranteed that it's going to be finished in the end. So that's something that I've been trying to discuss with the NanoHub team themselves, how they do their algorithms and stuff. But for now, that's the best option.
Maybe George can give you an idea about what's your estimate on running these kind of simulations?
Well, it's always a problem. I mean, unlike a lot of codes where if you're wrong on that, you can at least store some intermediate results and reinitiate the calculation. That's not something that is available. Well, in principle, it could be available, but it isn't available that I'm aware of. And so I mean, you really have to. Usually, what I tell everybody to do is just start with some toy model of what you're doing, and then just gradually increase the complexity of the model so you know how the time is going to work. Because otherwise you could really screw up badly in terms of that.
I mean, what's shown about the save option?
I just remember that. Thanks, George. Yeah, so definitely that's a very good point to start with a small model first, and at least make sure that that's running and that it looks good, at least for the small case. Additionally, NanoHub recently added an option, so I'll just run this so that it opens up. But there's this little button in the top right. So earlier we showed you guys can ask questions from here. It'll take you to the questions page or the tickets page. Also, you can save these simulations for later. So that's something that, especially if you've used this tool in the past, after 3 days or something, your tool will just automatically close, and you wouldn't be able to reopen your simulation. So now there's an option for that. You can just hit the Save Simulations option and give it a name, and it's kind of like a storage space. And so you can open an entirely different session, and you can open it in there. There's also one other feature that still is, I think it's unimplemented, which is to publish simulations. So that's another thing that NanoHub hopes to do, which is with all these tools and the results they're giving, in theory, they should be scientifically relevant, especially if the tool is being cited in a paper or something. Maybe there is some result that someone made in this tool that maybe they just have an image of, but it would be really nice for someone who's reading that paper to actually be able to like play around with that graphical simulation result, like looking at the E field on their own, moving those cut planes on their own. And so, that's something that's in development with NanoHub. They've been working on it for a while. So basically having like a way to publish these results in a way such that if someone goes to a certain URL, it'll open up this session with everything already run, and you can actually just go straight to someone's result and see it for yourself.
So the save simulation of Arcana Strength, you can, after you saved it, you can actually restart it. Is that correct?
Yeah, this is new. Yeah.
Not restart. You can look at your results. So the pre-run is already saved. You can restart if you want, but like what this view you see now, you see this view too. So all the results are already pre-computed. You can. So if you close this window, come back after 3 days, and you want to show the same results, you open load simulation.
Yeah.
It loads this one, and you can see the result.
Yeah, and additionally also, so within our tool we have the upload and download feature. So, I mean, we're kind of like on the forefront of tool technology. Like we have things that other tools don't have. So one of these things is the upload download, which is like if you had your own shape files or something that you made in a different 3D editor and you want to import it, you'd upload it. But what's really neat is that you can download. So this is like, so it automatically starts you out in the directory where you're running. So I didn't really run anything complex, so there's no files, but like you could find like shape files here if you wanted to download stuff locally. Since we were just talking about saving the simulations, that information can be downloaded basically, and you can give it to someone else. So although this feature isn't like, it's not, NanoHub hasn't really like published it yet, there is a way to give your results to someone else.
You can mention about collaboration downstairs. You can share the sessions.
Yeah. So previously, the only way to share was really at the bottom of the page. If you enter in someone else's username, they can share the same session with you. Like you can see their mouse moving on your screen and everything. But I think the future is definitely going to be in people collaborating. Maybe not in real time, but giving someone your results and letting them work with it, change it, do what they want with it themselves.
Any more questions? Okay, let's thank our speaker. Thank you.